Alberto. Thank you. So I have known Alberto since he arrived shortly after he arrived at Matt Mason's lab at Carnegie Mellon. He had done his undergraduate degree in Spain at the university in Catalonia, and he became quickly extremely well known among all of the alumni of Matt's lab as a rising star and very talented roboticist. And I was so happy to see the work that he was doing because he was really extending the theory that Matt had developed over the years and looking at problems like caging and planar manipulation and in-hand manipulation, dexterous manipulation it's sometimes called, and it made a number of interesting advances over the years. And he then did a postdoc at MIT with Russ Tedrake, and then moved to MIT, was hired there in the mechanical engineering department. He created a terrific new lab there, the manipulation and mechanics lab, that I have had the chance to, the opportunity to visit. And he's got a great team of students there. They have been turning out a series of fascinating papers. He's done work on really careful analysis, really great lab work, experimentation, pushing objects a million different ways and categorizing the outcomes to characterize the indeterminacy of frictional pushing. And they've developed a number of new mechanisms. They've developed ways of tactile gel site version that he may talk about. They've really been thinking in a very creative ways about how to manipulate objects. At the same time, he's also been very active. The team has been building working systems. So they took on the Amazon picking challenge. They were finalists and second place winners one year. They had in publishing their results all along, which I also appreciate. His work has been acknowledged by grants from Amazon and Google, National Science Foundation. He's gotten the RAS Early Career Award, number of best paper awards from the major conferences. And he is also, I have to say, also a terrific human being. He's a real, what we like to call mensch. And he with his wife actually are the housemasters of a major residential house at MIT, which is a huge responsibility, and he does that with charm, with his own kids, and he just always manages to bring everything he does with a sparkle and a special aesthetic touch that I think is really rare in our field, and you'll see it in his slides and the way he presents today. He's a great thinker, very creative mind, and I consider him a really good friend. So please welcome Alberto Rodriguez. Alberto.
Oh, wow. Thanks, Ken. Thanks a lot for that very nice introduction. It means a lot, especially coming from you. So I guess let's just go for business. And I hope you're seeing my slides. I guess thank you everyone for joining the talk, and especially thank you Andrea and Sam and Ken for organizing and making this possible. As I was saying before, I was scheduled to go to Berkeley in March, and unfortunately had to be canceled. So this is a great opportunity to be able to have a conversation. I know that Ken said that he will try not to interrupt, but feel free to ask any questions anytime. I much rather have a conversation than get to the end of the slides, so no problem there. The goal today, my goal today was to talk a little bit about some systems oriented aspects that I've been thinking recently that are involved in building dexterous robotic systems. And you'll see that the first half of the talk, it's more sort of maybe my thoughts on what is it that we have to do to move forward in manipulation. And the second half, I'll present some late results that we've been coming up in my group. Okay, so what's manipulation, right? So I guess the classical industrial view of robotic manipulation, which has been absolutely successful and has generated like dramatic impact in the world, in lab automation, in automotive automation, in warehouse automation. It's sort of this idea of moving objects precisely from here to there, one at a time. And it's almost always the case that we're moving things that we know how they're shaped in most cases, and we know where they are, and we know where we wanna bring them. And there's some repetitive motion that has to be executed. However, I think that sort of the idea that we have in our minds about manipulation, it's something that is much more flexible than sort of the implementations that we can see today. Something that sort of can handle the variability that, for example, you would find in my daughter's crafting table, right? So I usually like to go back to this example where, to me, everything that happens here is sort of what manipulation really is about, right? So whenever she or I or anyone at home sort of works in this table, like there's no instance where that is exactly the same as the previous instance. And every time we work with a piece of material, it's slightly different from before. We use tools that we're grasping them in different ways. And actually sort of novelty is rewarded, right? So you're actually looking for new ways to do things, for new ways to bend the world around us to our will. And it's that flexibility, that generality, or that adaptability of the skills that one might need to have to be able to work in a crafting table, that are so elusive that we actually haven't, I would say, we haven't made that much progress in the way that we might have made progress, for example, on more cognitive skills. So the kind of skills that are necessary to do, to perform at a 1 or 2 year old, what they would be able to do in a table like this are much, much more than what we are able to do today. And some degree sort of has to do with the fact that it's as much as engineering as it's an art, right? So we do it in a completely unconscious way of how we do it. And it's very difficult for us to sort of understand or appreciate, even when we're paying attention, how it is that we are doing what we're doing with our hands. Anyway, so I wanted to talk about that kind of manipulation today a little bit at the beginning. And I'll sort of have sort of 3 different topics today, right? First, manipulation, 4 different perspectives that I think that the community, the robotic manipulation community, has embraced when studying that problem. Manipulation primitives and the role that I think that they have to play, or the potential they have to play in bringing up these 4 different perspectives together. I'll sort of share some thoughts on what I think they are and what actually they contribute to building robotic manipulation systems. And then I'll describe those in the context of sort of 2 different research lines that we've been pushing forward in my group: dexterity with tactile feedback and dexterity with visual affordances. Okay. First, manipulation. And I think it was sort of February 2008, I think it was, that I went to Berkeley and last time. And I used this example in that talk, and I've actually used it quite a few since then, to illustrate what I think sort of a manipulation system that is dexterous should be able to do. And this is just myself sort of reaching into the bookcase and grabbing this book, and without any sort of conscious thinking, I engage in many things that have to do with mechanics, that have to do with haptics, that have to do with vision, and they have to do with planning and control, but that I'm completely unconscious about, but generate together a motion that is as fluid as something like this. I just go and I put my palm on the side of the book, and I pull backwards, and then I move maybe my thumb to the side of the book, and then I reach the grasp. And so I've been captivated for a while, but actions like these that are so fluid that it is very difficult to sort of describe what is happening, while at the same time there's a gigantic amount of complexity involved in replicating them. And I wanted to use this same example today to sort of illustrate these 4 perspectives that I think as a community we've embraced to study robotic manipulation. Okay, the first perspective, quite classic, right? So it's the mechanics control perspective, where we think of the object and the environment and the manipulator as simplified geometries, and we think of the interaction between them with simplified mechanics models. Can imagine the book is a plane, and the palm of the hand is another plane, and the thumb on the side of the book is a point, and each one of these, they have their respective Coulomb friction laws, and they're interacting with those laws, and then this generates a system that has to be controlled, and it comes with its own challenges, right? So there's an underactuated, partially observable system, and generating the control trajectories that are necessary to sort of bring the book back. It's a challenging problem, but it's one that has been embraced significantly, I would say, in the community, all the way from sort of grasp analysis to planning through contact. A second perspective, or a second way in which we could look at the action of picking up the book, is focusing on the haptic interaction between the palm and the book, but more detail at what happens at the interface, or the interaction, the exchange of forces between those two objects. Could be we have some force feedback capability, or we have some tactile feedback capability, but the goal there is to sort of monitor and possibly control, now with a feedback loop, that interaction. Maybe not necessarily being completely aware to the level that one would be in the mechanics control perspective of sort of the global aspects of moving the object, but maybe trying to sort of enforce certain relative motion between the palm and the book, right? So maybe the palm wants to stick to the book so that it can pull it backwards. And either sort of through force feedback loops or through tactile feedback loops, that's also a perspective that has been embraced by the community. A third perspective is where we think of moving the book as a sequence of actions, right? So maybe the first action is pulling it back, and sort of the book is moving sort of parallel to the wall. And then there's a second action where the book is pivoting on the edge of the shelf. And then there's a third action where the book falls into a grasp. And it's the sequentiality of those actions that go through those sub goals that generate long-term behavior that has been also the focus of a significant part of the manipulation community. And then a fourth perspective, maybe embraced more recently, I would say, especially in the last few years, is a visual counterpart to that problem, right? So we look at the book and we think, okay, what is it about the book, its geometry or its material properties, that makes the side of the book an interesting place where to put the thumb, and what makes the face of the book an interesting place where to put the palm. Clearly related to sort of visual affordances, and of course, sort of motivated and promoted by the uprise of neural networks, but nevertheless is a new or is another perspective on the same problem, sort of the visual-based approach. Now, I'm really not saying anything new here, right? So these are, we can think of these as, for example, a division on sort of approaches to manipulation based on the nature of the decision process, right? So maybe the decision process is model driven on the left, right? So we have some model of the mechanics, or some model of the a simulation model of the long-term behavior of certain actions. And the nature of the decision process could be driven by models, or could be driven directly more by sensing. Or we can think of these perspectives as divided by the locality or globality of the decision process, right? So maybe we're just looking at sort of the local interaction between the end effector and the object or the environment, or more globally as sort of the state of the task. And these are sort of classical divisions of the decision process in robotics. We can also see sort of how these approaches have been influenced by sort of assigning different types of value to what we think is interesting or challenging about the problem, right? So in the mechanics control perspective, we sort of acknowledge the fact that the interaction is driven through underactuated and hybrid frictional dynamics, and that generates difficult problems. So they're worthy of working on them, and they're worthy of sort of investing time. And that leads to sort of feed-forward control techniques to drive the state of the system. On the right-hand side, so we sort of focus or acknowledge that actually it is also sort of the exchange of forces and the exchange of velocities at that interaction that is important to figure out what will happen with the object, right? So no matter how much we how good we are at solving differential equations that are derived from the mechanics models, unless we are able to control the haptic interaction between the end effector and the object, there's not much that we will get done in terms of reliability or robustness. So there's also been sort of significant efforts along those lines, acknowledging that that is an important problem. Same thing can be said about sort of sequential planning, right? Where the goal or the worthiness is in deriving generality over plans for long horizon behavior, or in sort of the visual approach to manipulation, generality over percepts of objects and environments, right? So we want to come up with techniques that they don't work just for a specific object shapes or for specific models, but that can generalize over those tasks. And of course, all of these are important to manipulation, right? And all of these are worthy of working on, but really building general manipulation systems of the kind that arise at my daughter's crafting table do require integrating all of these perspectives, right? So, and in part is because of performance, right? We want high performance, but also because of, I will argue, simplicity. It is within sort of the interaction between these different perspectives that we can aim and target the simple solutions that can sort of lead to flexible behavior. I just realized that I'm not keeping track of the time. So just want to make sure that, okay, cool. Excellent. So something that to me is important to be able to address the integration between these perspectives is what we call manipulation primitives. And the role they play, I think that it is key in sort of cutting down or breaking through the high complexities involved in any of these problems. Any of these four problems, any of these four perspectives are extremely challenging if we try to solve them in full generality. And probably that's one of the reasons why we've sort of been attracted by these perspectives, because they're difficult. And one of the roles that manipulation primitives play is to sort of help focus or simplify the each one of these individual perspectives. When we focus, when we sort of look at the specific types of interaction between an end effector and its environment, we can make assumptions, and we'll get through these in a bit, about that particular interaction that can be exploited to simplify these approaches. And the second role that manipulation primitives play is in actually facilitating the integration between them. And the second part of the talk will be focused on two different research lines that we've embraced in the last couple of years in my group, sort of trying to integrate some of these different perspectives. But before that, I wanted to sort of have a little bit more of discussion on manipulation primitives and what they are. Okay, so how do they simplify or focus these individual perspectives? A manipulation primitive, right? So the key question is, how do we simplify the computational challenges that are involved in any of these? And the key idea that they promote is to restrict somehow, in some way, contact interactions. For example, by looking at particular interactions that have simple mechanics that are more easy to compute, or by looking at interactions that have efficient planners available to them, or that sort of render useful tactile information or useful visual information, right? So we make some assumption or some restriction and the type of interaction that the system is allowed to generate to be able to simplify the problem, right? So sort of the old idea of don't do that thing that you cannot control. So manipulation primitives are sort of a personification of that idea. So what is a primitive, right? So we can think of it, or one way that I like thinking about them is a set of assumptions or restrictions on contact interaction. For example, if we're forcing a sticking interaction between the palm and the object in this cartoon, and there's an expectation that the object will move with the palm, we call this sort of a pulling primitive. And it is that assumption of the sticking interaction between the palm and the object that reduces the complexity of the mechanics. If it's going to be sticking, we can think of it as sort of a quasi-static, that the object and the palm are going to be in quasi-static equilibrium. And if they're sticking under that assumption, then the motion of the object in the plane is a fully actuated kinematic system, right? So by moving the palm, I can move the object anywhere I want. That's sort of maybe one of the simplest types of assumptions that we can make. And that also helps clarify the division of roles when implementing systems. For example, what would be the role of haptic control? Well, precisely to enforce a sticky interaction, right? So if I have a controller that is in charge of making sure that the palm is always sticking to the object, then I can exploit that assumption for planning perspectives. And the role of haptic perception would be to track and making sure that whether the object is slipping or not in the palm. And if it slips, then sort of generate a signal. Okay, and like that, we could analyze different types of primitives that have been studied through decades, and they have indirectly been studied because of that, because sort of there are planners and controllers and trackers that are sort of available and are simpler than in the general case. Okay, so when it comes to restrict contact interactions, we have sort of done work, for example, on the mechanics control. So we can, by restricting to specific types of interaction, so that when we have a multi-contact system, only one of the contacts or can slip and not the other ones, we can generate compact friction contact models that then speed up the computation of mechanics. If we restrict to certain kinds of primitives, those are useful for planning because they simplify forward models. We don't have to simulate necessarily what's going to happen through that primitive, because that primitive comes with an expectation of what should happen. And that sort of simplifies or speeds up planning. Manipulation primitives also sort of, as we were saying, sort of can clarify the role of certain controllers, right? So we have a tactile controller here where the goal is to enforce a particular type of interaction assumption, right? So here the grasp is trying to make sure that the object doesn't slip. So if I pull from the object and the force is such that the object will not slip, the robot stays there. But if it detects that it's going to slip, it just moves away because it wants to enforce that particular sticking interaction. And finally, sort of from a visual perspective, having primitives also clarifies the role that they make. Instead of having to perceive objects, we perceive action relevant affordances, right? So here we're perceiving, for example, locations where it would be useful to go use the suction cap on these objects. Instead of trying to sort of estimate the pose of these objects, primitives determine what is the role of visual perception. So all of this just to say that when we decide to work with manipulation primitives, that has an effect on either simplifying or clarifying what is the role of each one of these aspects of a robotic manipulation system. But the sort of the key discussion that I wanted to have today is sort of how these primitives also facilitate the integration between these different perspectives. And I wanted to show two particular sort of recent works that we've done. First, on embedding tactile feedback in mechanics models. So trying to combine those two top perspectives, as well as a second one on long horizon planning with visual affordances. When we decide to have a perception system that is sort of targeted for specific actions, how can we engage that with sort of long horizon planning? Okay. Are there any questions before moving forward? This is sort of the end of the first part of the talk. And we will go now to the more sort of technical aspects. But before doing that, I'm happy to take any questions.
So I have a question, which is, I'm trying to relate this to sort of older ideas like, motor schemas from Arbeb or movement primitives from people like Stefan Schall.
Mm-hmm.
And of course, I mean, the notion of affordance is really not just visual. I mean, Gibson's notion of affordance was quite general. It really referred to a sensory motor loop. So, I mean, these ideas seem to be related. So the specific emphasis that you are putting is on being very specific about the contacts. Am I correct in saying that, or is there, yeah?
Yeah, so this sort of relates to what I guess, and it's not all perspectives. It's sort of 4 perspectives that I think that have been embraced significantly by the robotic manipulation community. But definitely robotics in general, or behavior generation in general, or if you go all the way to sort of studies of human behavior, there's many connections to these, but they're not necessarily one-to-one or a perfect match between them.
And I think maybe, Alberto, that when you say visual affordance, what you're really saying is that the affordance here is about what's going to allow you to lift that object. And in this case with suction, then that is transferred to points on the surface that afford lifting, as opposed to in visual, let's say recognition, the affordances might be edges or other features. So is that fair?
Yeah, exactly. So I meant sort of in the style that has been embraced, I would say, in the last 10 years or 8 years, where we're sort of building direct maps between visual appearance, visual in the extended sense. It doesn't need to be just RGB, it could be depth or some kind of sensory input that goes directly to a motor command in the form of usually a primitive, which could be pushing an object or it could be grasping an object. It has been implemented for the most part in the context of grasping and using suctions. But one of the topics that I'll discuss today is sort of how one possible way to generalize that idea to more dexterous manipulation primitives. But yeah, so the key idea there is that we sort of sidestep the process of doing state estimation, right? So we build a map that goes directly from raw appearance to action. I don't know if that answered your question, Jitendra.
No, I mean, I think I understand what you're saying. I was just trying to connect it historically to ideas which are not just in the robotics community, but in the broad sort of biological motor control, and like people like Gibson, which are sort of in vision and so on. And I think I understand what you're saying. Yeah, thank you.
Cool. Okay, so I'll go to the first sort of research topic, which is a possible approach or framework to embed tactile feedback in mechanics models, or tactile dexterity, and so to speak. And the idea is that if we go back to the definition of what's a manipulation primitive, some assumption and contact interaction that sort of might facilitate the mechanics model, or might facilitate the forward simulation of that behavior. The question here is sort of how does the primitive sort of facilitate the process of making decisions? And one key idea that we've been exploring is dividing sort of the role of tactile control, or this consuming this tactile feedback into two different decision processes, or two different controllers. The first one, what we call sort of the contact state controller, whose purpose is precisely to enforce that assumption, right? Manipulation primitive makes an assumption about interaction, which could be sticking, or could be sliding, or could be some form of force equilibrium in the interaction. And we have a controller whose role is precisely to enforce it. And then we have a second controller whose task is to exploit that assumption to move the object. In the case, or in the example of pulling the object that we showed before, in that simple example, the idea is there's one controller that is running that is just making sure that the palm sticks to the object, and if it doesn't, it will react to try to enforce it. And then there's another controller that it just leaves by that assumption, right? So there's a clear division of roles in the way that the robot generates behavior. And because of the assumption of this primitive of pulling in this case, generating trajectories or controlling the mechanics of pulling becomes simpler, as long as that assumption is sort of satisfied. Okay, so we've explored these sort of maybe intuitive division of roles in the context of a few systems. And this is one example. The idea is that there's a dual arm system with 2 palms, and both have provide tactile feedback. And I'll show soon which kind of tactile feedback they provide. But the idea is that we want to be able to generate this behavior in a reactive fashion. And the way that this behavior is generated is that the robot is executing a series of primitive interactions with the object. In this case, is a known object, is an object with known geometry. And each one of these primitives is executed in a sort of closed loop fashion. So first of all, the type of feedback we get, this is sort of a version of gel-side that has sort of this wedge shape to facilitate interaction, but it's the same idea. There's a camera inside the palm that is looking at the deformation of a skin of a gel, and by sort of visually tracking the deformation of that skin, we can estimate geometry, and we can estimate shear or forces at the interaction. So on the left, you can see sort of the edge of the object. So this is a very structured setting where the object is sort of cuboidal, so that it's easier to know what is it that we need to track in the palm. And on the right-hand side, you see sort of how the sensor is sort of tracking when it's slipping versus when it's not slipping, or sort of trying to estimate contact forces. In this case, it's always slipping. But the idea is that with this type of sensor, you can capture both things in real time. Now, if we have access to that type of information, going back to the division of roles of these two controllers, we can derive an object state controller whose task is to replan trajectories for the motion of the object, right? It sort of exploits the assumption of sticking to continuously replan how to move the object to a particular desired location. And because it exploits that simple mechanism, it can replan fast enough. And then there's a second controller whose task would be to just sort of monitor the downward force to, if it detects that the object is about to slip, it will try to exert more force. So now on the left-hand side, if we sort of perturb the object, the robot will try to bring its current best estimate of where the object is. In this case, it's sort of an implementation with just tactile feedback to the goalpost. And here's a second controller where, depending on whether the object is slipping or not, this sort of modulates the gripping force, or in this case, the downward force. And then in general, sort of the first controller, it's very primitive dependent, right? So every primitive, based on the assumption that it's making an interaction, it will have access to its own controllers. If it's pulling, it's just a purely kinematic trajectory, but if it's pushing, it would need to use a different controller. If it's grasping, it will use a different one. And the contact state controller, we can think of it in a more general fashion. And the idea is that we have a multi-contact setting, and we want that multi-contact setting to remain constant. We want it to be in equilibrium. We have a model of, we can derive a model of the robustness of this multi-contact setting by approximating it by how far or how close are each one of these contact forces to the edges of their respective friction cones. Is the distance between the contact force and the edges of the friction cones that sort of captures the robustness of the multi-contact configuration. And we can write this. This is a sort of a standard formulation, very quite similar to the one used, for example, in the locomotion community, where we try to maximize this margin of stability, or the distance of the contact forces to the edges of the friction cones, subject to sort of force equilibrium. We want to make sure that the contact forces are always balancing the external range, in this case, just gravity, or possibly also external contacts with environment, and subject to just sort of Coulomb friction law. And this defines sort of an optimization problem that we can't really solve in real time because the margin is non-convex, has a trigonometric expression, and the force equilibrium condition is bilinear, right? So in this problem, what we're going after is sort of what are the changes in the contact forces as well as the contact locations or orientations of the palms that maximize the margin of the margin to the edges of the friction cones. And because we can change both the, I don't know if you can see my mouse, but the Jacobian as well as the contact forces, this is a bilinear constraint. It's sort of difficult to optimize in real time. So we do some convex approximation of the margin and linearized around the current configuration to be able to solve this in real time. And with that, we can sort of implement it in almost real time. And this is the kind of behavior that you get when you put both controllers together, right? So this is a regulation task where the robot is trying to maintain the object in that center configuration, and when we're perturbing it, sort of it's adjusting the downward force, and at the same time it's sort of replanning sort of trajectories for the object to bring it to the goal configuration. And then when we put these together for different primitives, all of them sort of executed in a reactive fashion with their own object controllers, but with the same contact state controller, we can build a system that sort of chains sequences of executions of manipulation primitives to change the location of an object from configuration A to configuration B in a reactive fashion. Reactivity just at the primitive level, not at the planning the sequence of primitives. And the key idea here is, again, that division of roles between the having two controllers, one that is in charge of enforcing a certain assumption that is dictated by the primitive, and then another controller that is just exploiting that assumption to move the object. Now, this sort of division of roles can be sort of used in different contexts or in different manipulation scenarios or with different primitives, and not necessarily just for sticking, but also, for example, for sliding. Here's another system where that we built recently to manipulate cables, and it's again purely driven by tactile information. There's no vision here, and the goal is to get the robot to sort of slide its fingers along a particular cable. And the way that this system is able of doing it fast without sort of having to rely on vision to do a state estimation of where the cable is in real time is, again, using exactly the same division of roles for two controllers. One controller that is in charge of controlling the position of the cable in the fingers. The orientation, controlling the orientation of the cable in the fingers, as well as sort of the position along the length of the fingers. And it's doing that by using the real-time estimates from the tactile sensor and the orientation of the cable. And it's doing it also by exploiting sort of the assumptions or exploiting sort of the having the benefit of having a parallel controller on its side that is monitoring, it's controlling the gripping force on the cable so that the fingers can slide smoothly along the cable, right? So that's a task that without some real-time accurate gripping control, it would be difficult to do, because if you apply just a bit more gripping force, the cable would get sort of stuck on the fingers. And if you apply less force than it's necessary to maintain it there, the cable will fall. It doesn't matter what the fingers do to be able to recover it. If the fingers open or don't apply a certain amount of force, the cable will fall. So by combining a controller that is just looking at the gripping force and it's just making sure that the frictional forces when sliding the fingers are within a certain range. That's pretty much what it's doing. It's just looking at the shear forces, at the average shear force in the fingers. And if it's too large, it will open up the fingers a little bit. And if it's too small, it will close them a little bit. And it does that in this implementation at 30 hertz. And now that is sufficient for the dynamics of the interaction between the cable and the fingers to be simple enough to be always within a certain dynamic working point where the interaction between the cable and the fingers can be modeled by a simple linear model. And here you see the kind of feedback that we get in terms of estimation of the cable, as well as the frictional forces. And each one of these type of feedback will feed into one of the two controllers. Now, we make a simple linear model, which we sort of estimate with capturing some data. And then we use an LQR controller to keep, where basically the goal is to keep the cable centered on the fingers, right? If the cable is moving to one side, it will sort of, the fingers will compensate trying to keep it in the center. And then there's a second controller that is basically just a PD controller to maintain the friction level while the fingers are sliding. And it's the combination of these two controllers now that generates this smooth behavior, where in one direction, the fingers are moving horizontally to try to keep the cable in the center. And in the vertical direction, the fingers are sort of closing fast enough to maintain a certain amount of friction. And again, it is precisely sort of the assumption of this primitive that in this case that the cable is sliding, that is on one hand enforced by one controller and on the other hand exploited by the other controller. Now it's not in a model-based fashion, but it's or the model is directly learned from data. But it's that simplifying assumption of the primitive that makes this possible. Any questions?
Hi, yeah, I have a question.
Sure.
Sorry if I missed this. How are you estimating forces for your gel slim sensor? Is there a separate force sensor in the gripper, or?
So I guess more or less all of these sensors work the same way. So I'll just illustrate it in the case of this sensor. Inside the sensor, there are these dots embedded in the gel, and by tracking the location of these dots, we can estimate the displacement of the skin or the stretching of the skin. And then you can go the extra step, which we do in sometimes of sort of using inverse FEM to estimate the force distribution.
Mhm.
But actually, in this case, it turned out that that wasn't necessary. Just by using a proxy for friction, which would be sort of the average deformation of the skin, that was sufficient to control the system.
Oh, I see. Okay, so I guess so you're using a friction model essentially to back out an estimate of the force. And
so actually, in this case, we're not even doing that.
oh, okay.
We are directly regulating the gripping force, not to maintain a level of friction, but to maintain a level of stress on the
On the skin.
on the skin. Yeah.
Oh, okay. Got it. Thanks.
Cool.
I have a question. I'm wondering, are you translating the, so it looks like in the tactile dexterity and the cable manipulation, the feedback is being applied in the end effector space. And I'm wondering if that's the case, or if you're applying it to the joint space, and depending on which direction, how are you avoiding like kinematic singularities and other limitations?
Yeah, that's a fantastic question. So like everything that I've described is sort of micro looking at what happens between the end effector and the object, but the end effector is moved by arms, right? As you were saying. And so all of that has to be eventually transferred to, and there's a lot of engineering that has to do with that. We're not using anything that is sort of new. We're using, for the most part, just good old-fashioned engineering in terms of using sort of inverse dynamics and fast IK and different packages that are available to do real-time planning. And so for most of the primitives, what we have to do is to sort of pre-compute beforehand nominal configuration of the arms that give us enough sort of range of motion so that inverse dynamics or inverse kinematics is sufficient to do replanning in real time, because we have to replan very fast, right? So we cannot just use sort of arm planning in real time. But that's that sort of takes care of motion that locally. If you need to do large reconfigurations, that comes at a higher cost, and we sort of deal with that in the second part of that I was going to describe today. But I'm not sure that we're going to get to it, looking at the time.
We are running on the late side, Alberto, and I want to give you enough time to finish. I also do have a question too, which is,
sure,
maybe this relates a little bit back to Tender's question about vision versus touch here, because I'm just curious what your thought is. Would vision be sufficient? Could it? Do you think that cameras would be sufficient to allow that similar kind of very elegant motion that you're talking about, being able to detect and compensate for the slip of the cable?
Mm-hmm. I mean, I guess I can give you first the trivial answer, which is that this is done with cameras, right? So it is a camera inside the fingers that is capturing this signal. But more than that, I think that the point is that there are some interactions where what matters, the way that you describe certain tasks, it's not in the language of poses or in the language of sort of configurations in a normal configuration space, but you want to describe it in the language of forces, right? So in this case, I want my controller to keep a certain stretch on the skin to be able to slide my fingers. So how do I do that with like an external camera? I don't know, right? Both the way that I describe the task and the way that I implement the controller require using that language that is not directly the pose of anything in the world. It's a deformation, it's a stretch, or if you want, a force.
Okay. Well, we can talk a little bit offline. We'll have some more chance to do that. But I want to give you a chance to wrap up, because I know some people have to go. But thank you. Go ahead.
Yeah, so I'm just gonna, I guess, just give a highlight of the second part. The idea is now, there's been a significant amount of work on what we were discussing before, visual affordances, right? So triggering behavior directly from visual observations of geometry or materials. And all of that has sort of generated like amazing, reliable performance, especially when it comes to deal with clutter and when it comes to deal with the large variability of objects, right? So in the Amazon Robotics Challenge, but also in a lot of research that is doing at Berkeley, for example, learning using neural networks to learn directly maps from raw perception directly to action in the form of manipulation primitives has shown amazing behavior. And of course, the caveat that comes with that is that because we're operating directly in raw perceptual space, we don't have the ability, or we don't have the ability to exploit what the primitive, one of the things that primitives give us, which is sort of an expectation of what will happen with that object, right? So we don't have necessarily forward models to be able to predict how the state will be after executing that action. And there's a lot of work going on these days on sort of computing or learning like foresight models for what the perception will be after executing a certain action. And to me, that is sort of a key challenge that we need to address, how to merge these sort of visual affordance models with planning so that we can do sequential decisions to generate sort of competent manipulation systems. And I'm just going to skip these, but the idea is that we've been sort of looking at different aspects of sequencing manipulation actions, but always without necessarily having an explicit model that predicts what's going to happen. This is using sort of deep reinforcement learning to sequencing pushing and grasping, or to sequencing grasping and tossing. But the idea is that all of these implementations explicitly avoid having to do a forward prediction of what will be the state in perceptual space after executing a certain action. And when it comes to solving problems like the one that I showed before on a tabletop scenario, doing that without having a forward prediction model sort of is quite limiting, right? So if you want to be able to plan a sequence of actions like this, like a pull and a grasp and then a push, it is very difficult to do it without, or a pull in this case, without the ability to predict forward how the observation space will be after executing each one of those primitives. So one of the things that we've been doing is sort of find a way to be able, defining a framework to be able to do that. And again, the idea is to exploit sort of manipulation primitives and the assumptions that they make. We need to sort of expand this notion of affordance from just locating a point in RGB space to having a more precise model that predicts contact locations. And then we need to have a predictive model so that we can change subgoals. For example, to plan this sequence of pull, grasp, push. And I'm going to skip some of these so that we get to the end. But the basic idea is that I'm going to go to the key idea slide, is that we use a representation of objects in the form of rigid body point clouds, right? So for us now, objects are a segmented part of the point cloud directly in observation space. And we constrain ourselves to just using primitives where the contacts are sticking to the objects. And by sticking to the objects, that in combination with the representation of the objects, it gives us a natural way to do a forward prediction or forward propagation of the implication of executing a particular primitive. So we learn an affordance in the form of a map between a segmented part of the point cloud and where we should contact that segment of the point cloud, and what will be a useful subgoal that now is compatible with sort of the reachability of the robot, with collision avoidance, and with everything that might prevent the primitive from executing. And we put all of that weight, all of that effort in modeling those constraints or those limitations on the affordance model. Now, we learn in simulation where is it a good idea to contact objects to execute particular primitives, and what are useful subgoals where to bring objects, and we use a variational autoencoder to do that. And then during planning, we use this model to generate samples of contact locations and subgoals, which then these can be sort of embedded into a normal task and motion planning framework to do to solve problems like this. Like if the goal is to bring this object, which for the system is nothing else than just a point cloud, there's no model in this case, to the green configuration, it sort of decides to grasp it in a different way because the final configuration and the initial configurations are different. It's compatible with sort of long sequences of actions, right? So like in this case, we're telling it that it should pull, and then it should regrasp, and then it's pulling again, and then it's bringing the object to the shelf, and then it's bringing it to that final configuration. And because this is driven directly, and this is, I would say, one of the most important points from raw observations of the point cloud, the affordance models have the ability to generalize to different geometries beyond what you would expect from a normal planning model. So in this case, is one of the objects from the YCP dataset, and it still sort of figures out that it can bring it to the center and then re-grasp it.
Alberto, it's Ken. I'm so sorry, but I'm going to have to head over to the other meeting. But
Okay.
But I think this is great for you to stay here. I think we should take a moment to thank you on behalf of all of us for sharing all of this with us. And I will I look forward to seeing you back in my lab meeting in approximately 20 minutes or something like that. But the others will stay, and happy to answer questions. You've got still 40 people here, which is far more than we normally get on the Monday seminar. So you're doing great. All right.
Excellent.
Thank you again, Alberto. Talk to you later.
Thanks, Ken.
Okay.
Talk to you.
Okay. Bye.
And this is just the last video, just showing that because we're using point clouds, there's also sort of it has an easier job at sort of generalizing to real world observations. The system has never seen a bottle like this. It has only been trained on cuboids, but it still sort of has the ability to plan the sequence of actions. Okay, so this is the end of the presentation. Sort of 4 different perspectives on manipulation, on robotic manipulation, and the key idea that sort of dividing manipulation into manipulation primitives simplifies computation and allows integration of some of these perspectives. And I showed a couple examples, how to use tactile feedback into mechanic models and how to do planning with direct visual affordances of geometry. And I just wanted to highlight Francois Hogan, who is the main author of the tactile dexterity work, and Anthony Simeonov, who is the main author of the planning work. Excellent. And I'm happy to take any questions.